Welcome to This Explainer. Today we're diving into a bit of a biological detective story. If you track your metabolism or you follow ketogenic science, you hear the word ketone literally all the time. But get this, there is a massive misconception hiding right in plain sight. We're going to look strictly at the source material to unpack the real chemistry of ketones, and I promise you, it's going to completely change how you view your body's energy systems. So, here's the big question. Is the ketone you know actually a fake? I know, it sounds super dramatic, but it gets right to the heart of our mystery. Think about it. Millions of people prick their fingers or breathe into these tracking devices every single day. But what if the primary molecule those meters are tracking isn't even a true ketone? Well, to understand this imposter, we first have to wrap our heads around the rigid laws of the molecular world.
All right, Section 1, the true chemical meaning of a ketone, the strict rules of chemistry.
So, in the discipline of chemistry, there is absolutely no gray area. Structure is absolute law. For a molecule to officially be called a ketone, it has to have a very specific arrangement. You'll notice a central carbon atom, that's the C, and it's double bonded to an oxygen atom, the O. We call this the C double bond O, or the carbonyl group. Plus, this central carbon has to be flanked by carbon-containing groups on both the left and the right sides. Those are represented by the R and R prime. If a molecule doesn't have this exact R-C-O-R structure, chemistry just crosses its arms and says, nope, absolutely not a ketone. And looking at the source material, this brilliantly illustrates just how strictly that C double bond O rule applies, even across totally different molecular shapes. Let's look at 3 classic examples. First up, we've got acetone. It's the simplest ketone and perfectly mirrors that straight line formula. Next is cyclohexanone. Now, even though this one forms a hexagonal ring, that crucial C double bond O is right there, baked into the shape. And finally, acetophenone, which attaches that same C double O structure to a complex benzene ring. The takeaway here? No matter the shape, straight line, ring, complex appendage, that mandatory C double bond O is always present. It's the ultimate hallmark of a true chemical ketone. Moving on to Section 2, our body's 3 ketone bodies. What the body produces. Okay, so when we switch gears and look at human physiology, we find that our liver produces 3 specific molecules that we broadly call ketone bodies. You can see them right here. Acetone, acetoacetic acid, which is also known as acetoacetate, and finally, beta-hydroxybutyrate, or as we all know it, BHB. Now, if we apply those strict chemical laws we just learned, acetone and acetoacetate, they pass with flying colors. They both contain that non-negotiable C double bond O flanked by carbons. They are chemically pure ketones. But what about that third one? Which brings us to Section 3. Is BHB not a ketone? The imposter revealed. Here is the crazy part. The most famous ketone body, the exact one everyone talks about on a keto diet, BHB, structurally violates the chemical laws of ketones. It completely lacks that mandatory C double bond O. Somewhere along the metabolic pathway, that vital double bond was just stripped away and reduced into a hydroxyl group. So, by the strict, undeniable definition of chemistry, BHB has entirely disqualified itself. So, we're left with this fascinating conflict. On one side, we have chemistry's super strict view. Because it has that hydroxyl group, chemistry classifies BHB simply as a hydroxy acid. It is literally not a ketone. But on the flip side, we have physiology's practical view. Biology goes ahead and categorizes BHB as a ketone body anyway. Why? Well, because the body doesn't care about the naming conventions of human chemists. It cares about function. BHB is created in the exact same metabolic pathway in the liver as the true ketones, and it performs the exact same energy-delivering function. It's basically an honorary member of the club based entirely on what it does, not how it looks. Section 4. Why does the body make BHB? The mitochondrial engine. Inside the mitochondria of your liver cells, there's this very specific 3-step manufacturing process that takes place. First, a true chemical ketone, acetoacetate, meets a molecule called NADH. Second, an enzyme with a remarkably long name, beta-hydroxybutyrate dehydrogenase, swoops in to act as the catalyst and spark a reaction. Third, this reaction physically alters the acetoacetate. It reduces it by swapping out that C double bond O for a hydroxyl group. And the result? The creation of our imposter, BHB, along with the leftover molecule called NAD+. It's wild, right? The body takes a perfect ketone and intentionally modifies it. Now, for anyone practicing metabolic therapies, this right here is absolutely crucial.
When you're fasting or adhering strictly to a ketogenic diet, your liver experiences a massive spike in NADH levels. And if you remember from just a second ago, NADH is the exact fuel required to drive that conversion process. So when those NADH levels skyrocket, this whole enzymatic machinery goes into absolute overdrive, just furiously converting acetoacetate straight into BHB. And because this conversion process is running so incredibly hot during fasting or keto, BHB ends up making up a massive 70 to 80% of the circulating ketone bodies in your bloodstream. I mean, really think about that for a second. Up to 80% of your so-called ketones are actually hydroxy acids. Mind-blowing for sure.
Let's head into Section 5, Why We Measure BHB, the process of elimination.
So you might be wondering, why on earth don't our standard fingertip blood meters just measure the true chemical ketones? Well, it's basically a process of elimination. Acetone is so volatile that it simply flies away. It escapes our body through our breath, which, by the way, is exactly why some people get keto breath. Then you have acetoacetate, the other true ketone. It's highly unstable in the blood, constantly breaking down, which makes it a total nightmare to measure accurately and reliably. But BHB is highly stable. It sticks around, and as we just saw, it has by far the highest concentration in the bloodstream. By default, it's literally the most reliable marker we have. So the crucial takeaway from the source material is this. When a doctor, a nutritionist, or an article tells you your blood ketones have increased, what they almost exclusively mean in clinical and practical terms is your blood BHB concentration has increased. Our entire modern language around tracking fat burning and ketosis is completely reliant on this incredible, stable energy provider that, ironically, isn't even a ketone. This matrix right here brilliantly summarizes the entire core conflict. Look at acetone and acetoacetate. Are they chemical ketones? Yes. Are they physiological ketone bodies? Yes. They tick all the boxes. But look down at BHB at the bottom. Is it a chemical ketone? No way. It strictly fails the structural test. But is it a physiological ketone body? Yes, absolutely. It perfectly bridges the gap between rigid chemistry and the dynamic, functional needs of human biology. Because at the end of the day, in the world of the human body, it doesn't really matter if you technically wear the badge of a ketone according to a chemistry textbook. What actually matters is if you can step up, flow through the bloodstream, and deliver vital energy to a hungry brain and body when carbohydrates are scarce. BHB might be an imposter on the chemistry's chalkboard, but inside you, it is the undeniable champion of human metabolism. So I'll leave you with this to chew on. Does human biology ultimately prioritize practical function over strict chemical form? Thanks for tuning into this explainer, and I hope it gave you a whole new perspective on your metabolism.